Hello? Okay. So I want to take up one paper, which is a very recent paper. It was presented at Coral, and there is a YouTube video for it. And I like this paper a lot. I mean, of course, I'm sure we can find holes in it, but it has various components which I think are quite sensible of how to do this. So what I'm going to do is I'll take you through this, and actually I'm going to uh, just let the video play because I don't need to repeat a lecture when. Okay, so what they do is their range of tasks is not as fancy. Okay, it's sort of more classical type robotics people's tasks like opening a drawer, picking up an object, dropping in, and so forth, right? So the list of tasks is not as exotic as we saw in the Google demo or a Pi demo. However, what I like about it is that it it does have generalization. It has generalization across objects, which to me is important. And I think it has robustness, but for a much smaller set of tasks. The hardware is not more general. It's still parallel GeoGripper. So from that perspective, my complaints still apply. It's slightly different. I think this is the Shuran Song version, the Umi, which has slightly different. It's got like another camera, so you get the equivalent of a stereo view. And I mean that we don't need to go into that detail, but it's a slightly different hardware setup. Uh, okay, so just to repeat what they say, they also connected to language models in a fairly sensible way. So you use the language models to create to have a high level plan, and then you have, if you consider the components of that plan, those are going to be skills, right? Like pick up, put down, open the drawer, things like that. So then that becomes that you condition the policy on that. So from the plan you get the individual actions, and then the policy is conditioned on that action, which is very sensible. Okay, so let's see if this. So I'm going to play this. I apologize because that instead of giving a lecture, I'm letting you watch YouTube. But
Hi, everyone. My name is Murtaza Dalal. I'm a PhD student at Carnegie Mellon, and I'm very excited to talk to you about our work on building generalist agents for robotic manipulation. This was work done with my co-lead, Min Liu, collaborators at Apple, and of course, my advisors at CMU. As a teaser, I want to show you our final result, ManipGen, a single generalist agent across manipulation tasks. This is a text-conditioned agent that performs zero-shot, long-horizon manipulation. We deployed on 5 different tasks with a variety of different setups, which I show here. I really want to emphasize these tasks are quite difficult, much harder than what you would see normally, because these scenes are extremely complex,
I mean, to
with
me, these
many
scenes are much
obstacles,
more real
objects,
than the
and
ones in the
receptacles.
video.
This single agent has to perform collision avoidance, generalize to arbitrary objects, and perform constrained manipulation. All of this completely zero shot, just from text input. So you might be wondering, how did we get here? Well, that is going to be the focus of today's talk. So let's start off with some motivation. Let's watch this video of a person opening a door, and you'll see that there's clearly 2 stages. One in which we reach a pre-contact pose, in this case the door handle, and then there's contact-rich interaction, actually turning the handle and pulling open the door. Maybe we can use this idea to decompose manipulation tasks? Let's instantiate this by defining a new policy class, local policies, as policies that are initialized close to the object of interest or interaction point.
Okay, so let me pause here. I mean, this is the same thing that I've been pushing for a while, which is the notion of a skill, which is at the unit of 1 second. This is also consistent with what we know about how children learn. So their initial phase is that they reach, but they cannot grasp. So if you see kids in their cribs, they're just, their hands are flailing about, but they basically manage to reach an object and then they push it, or it shakes or makes some noise or whatever. They're not ready yet to make grasps. That comes later. So they call this, in that literature, it's called the reach phase followed by the grip phase or the grasp phase. So and we talked about it earlier when we were discussing insights from child development. So this breaking up into phases is very natural. And so anyway, let me continue.
Initial state distribution. They take in local observations just in the vicinity of the object or interaction point, and take local actions in that region, aka relative actions. They look something like this. These local policies have some great properties. They're invariant to absolute pose because they only care about the relative positioning of the hand and the object. They're invariant to skill ordering since we can use motion planning to take care of the chaining problem. I'll talk about this in more detail later. And finally, and most importantly, they're invariant to the global scene configuration because they only care about the local region around the object.
Okay, so let me comment here. Why do I like this? So what does that condition do? XE is about the end effector, and then the tar, right? So it's essentially you're going to have a stage where you get to the location where your hand needs to operate on the object, and then there's a transport phase. So now you've got modularity. So this modularity is what we did when we were doing navigation, right? So you can have modularity, you can have obstacle avoidance dealt with by other methods. There are many techniques which will do obstacle avoidance, classical techniques and neural techniques. So in that process, you've got robustness to the varieties of different scenes that you can have, because the rest of the scene doesn't matter. You get to the object of interest, and then you're going to do stuff with it. Like maybe you're going to pick it, maybe you're going to throw it, whatever. Okay, that comes at the end. Now these modular skills can be composed together. They're calling these skills local policy, but I call them skills. Okay, this is not, there are challenges with this, right? Because sometimes the errors can accumulate, and what you need to do is that there needs to be some preconditions which are specified before you can execute a skill. But a couple of years ago, I had a paper with Devendra Chaplot and a student intern and Hausu, which was essentially on how this composition of skills can work. You need to, when one skill ends and the other skill begins, you need to be in the correct configuration. That's the condition that you have to do, and after that, you can actually chain together many steps. Not just, because chaining always means that you're reducing your probability of success. But if you are careful about this, it can be done quite well. End-to-end policies suffer from the combinatorial blow, because now you have to train end-to-end policies for all the exponentially many combinations of skills that you have. I think when you train skills, then it just becomes linear in the number of skills. Okay.
Means it's much simpler to generate data for them at scale. The core idea of ManipGen is that these local policies enable us to scale learning for manipulation in simulation and transfer it to the real world in a modular structure to solve a wide variety of different tasks. As an overview of this work, ManipGen first uses RL to acquire local behaviors at scale. Then we distill these thousands of experts into a single visual motor policy per skill. And then finally, we deploy these policies zero-shot in challenging environments by using a VLM to plan, a motion planner to reach poses near objects, and local policies to perform manipulation. So how do we actually acquire local behaviors using RL? Well, for the observations, we found it important to include a significant amount of privileged information in this phase, which we do so by incorporating shape information and components of the reward. For the reward itself, we have a general formulation that looks something like this. Here, REE, ROBJ, and RSuccess specify the behavior of the skill, while the other two rewards constrain the motion of the policy making it easier to transfer sim to real. Now, putting everything together, we pass the privileged and proprioceptive state information into the policy, and we train these policies using PPO at scale.
Okay.
To
so
see
let
our
me-
local policies in action, check
Okay.
out the
Okay, let me pause there and okay, let me comment here. So if you a good example to think about this is the work we had on rotating objects. So I think we talked about this earlier, House's work and Toru's work, rotating objects. What do we need for that? You need to know something about the shape of the object, right? And this is something which at execution time is going to be estimated with the help of cameras or cameras plus touch or cameras plus touch plus proprioception. I mean, so my claim here is trust perception. Perception can do something. Perception, computer vision people are not idiots. They are able to achieve some goals and they can pull something out. Okay. When you do training, what do? This idea of privileged information is a very useful one. And this has been very successful in locomotion. So the version of that here is that you have some low dimensional representation of the shape. So maybe you have the shape and then you run it through some autoencoder or something, which makes it lower dimensional, and you feed that. Generally speaking, motor policies like manipulation or locomotion, they do not need exactly all the details of the environment underneath your feet. They do not need exactly all the details of the shape of the object. There's an approximation of the shape which is good enough from which you can act. And that's what you want to capture, right? You can do that at training time, then it's privileged information. At test time, you're going to rely on your sensing from vision, touch, proprioception to do the best job possible. So this philosophy we saw earlier in the work of rotating objects or removing lids and so on. You see a version of exactly that same idea here. So this is a robust idea. I mean, let me say, I like this idea a lot. Okay, let's keep playing.
At scale.
And always we just run
To see our
PPO,
local policies in action, check out these videos of the pick, place, grasp handle, articulated object opening, and closing skills. For pick and place, we sample random clutter and distractor objects and encourage the agent to only interact with the target object, here shown in red. One thing to really emphasize here is that due to locality, we can make the simulation environments dead simple, but we can still generalize to complex, real-world scenarios. The reason this is possible is that we are invariant to global scene configurations, since we only observe things locally. Now that we've acquired behavior, we need to distill all of these single task experts into a single generalist policy per skill. The key to doing this is using online imitation learning. Since RL policies can give us dense feedback at any state, they're queryable experts, so we can just do multitask dagger. Now, for the observations, we opt to use wrist camera observations, which are of course local. Once the policy gets super close to the object, it might have some difficulty in telling what's going on. So we also incorporate the first frame, which generally has a clear view of the object. We also need to communicate which object to interact with. So we pass in a segmentation mask of the target object, which we can easily get in the real world using grounded SAM. Now, for local policies, we found that you actually don't need an enormous sequence model to fit the data really well. So here we opt for a ResNet 18-based architecture with a spatial softmax at the end, and then we use an MLP decoder to predict delta and effector control actions and just train with MSE loss using.
Yeah, so I mean, this part feels similar, right? You've got cameras and so on, but there is a specific thing of using computer vision in a more sophisticated way. So they are using grounded SAM. So computer vision techniques for segmenting objects, labeling objects. There's no reason to do everything end to end. I mean, in the previous lecture, you saw everything was being done end to end. So as if the only vision which you need to learn is in the context of this task. Whereas what this is saying is, hey, there is all this work that the computer vision community has done. Let's make use of it. Okay.
Multitask dagger. So now the question becomes, how do we actually deploy these visual motor local policies in the real world? For that, we build on prior work on plan, sequence, learn, which used a hierarchical decomposition to efficiently train specialist policies for challenging manipulation tasks. A quick sidebar. PSL uses an LLM to decompose the task specified via natural language into a coarse high-level plan. It then uses vision and motion planning to actually step through the plan, which is done by estimating the pose of the target object and then motion planning to it. Finally, it uses RL policies to efficiently learn local.
Yeah. So let me pause here. I mean, again, I think this is the idea of a hierarchy, right? As opposed to just end-to-end learning of for every task. There's a hierarchy here. The hierarchy is very sensible. At the highest levels of the hierarchy, you use language. Language is great for capturing goals and sub-steps of plans. Then we are trying to get to sub-steps of plans. This is where vision comes in, because the sub-steps of plans will typically involve, poses and how you interact with an object, and different poses you'll interact with in a different way. So your sort of computer vision, 3D, all of that kind of stuff comes into this stage. And then there is the actual motor policy. And here, instead of just designing it, we are going to try to learn it. We can use different ways of learning it, which we can use, there's nothing wrong with supervision, but in this case, once the task becomes simple enough, reinforcement learning is a good approach. And reinforcement learning, the value, why I like that is because robustness and generalization can in some sense be built in, because you can put in noise, you can have different kinds of shapes, etc., etc. So the scaling law, you need diversity, but that diversity here is in the training environment. We're not relying on the diversity coming from the human teleoperators.
Interaction. However, this is all done in the loop to learn a specific task. The core challenge now is moving from the specialist approach to a generalist approach for manipulation. For each step, we will use learning at scale to build generalists with specialized capabilities, and then combine them to massively amplify their generalization. First, to perform real-world task planning, we need the agent to perceive the environment, which requires the use of some sort of a VLM instead of an LLM. Here we use GPT-4o, as we found that VLMs trained on internet-scale data perform quite well. Next, for fast, reactive, real-world motion planning, we want to use a motion planner that can operate on noisy point cloud input. Here we use neural motion planner, an end-to-end policy for performing fast motion planning in the real world. Finally, we come to the core new piece of ManipGen, which I just described. To train generalists that can solve new tasks in a zero-shot manner, we need pre-trained skills, which we obtain by scaling up learning in simulation and transferring sim to real. Having defined all of these components, let's quickly walk through an example deployment. Here we use the VLM to come up with a plan for the scene given views of the scene and text prompt. It comes up with a plan in terms of the skill library using the formatting I show here. We then deploy this plan open loop, estimating where to go using grounded SAM to segment the target object point cloud, averaging it to get a position.
Okay, I have to repeat my claim that skills, these are the essential components. So here, if you see, all of these are skills. So it's open, and that's a skill. Pick is a skill, place is a skill, close is a skill. And then these skills are parameterized because they have to do something different for each object. So open, handle, pick, rise, and so on. So the basic components of human action are, there is a subject, verb, object. So the subject is the agent, me, the human. The verb is like open or pick, and then there is an object on which I'm acting. And sometimes there can be two objects because there is a tool and then there is something you're operating on. This is the basic vocabulary of action. This is the basic vocabulary with which to interpret video streams. This is the basic vocabulary with which to act in the world. It's common sense. To me, this is not rocket science, but Voltaire said that common sense is very uncommon. Okay, so let me continue.
Collision-free poses that point at the object. We alternate between pose estimation, neural MP, and running the right local policy until the task is solved. Okay, let's quickly look at some results. We evaluate ManipGen on 5 different diverse tasks. achieving high success rates across each task, at least 60% on the hardest, long horizon tasks, with up to 90% on some challenging multi-stage manipulation tasks like storing items in the cabinet. Our tasks are extremely challenging, requiring the agent to perform pick and place, articulated object manipulation, constrained tight space manipulation, all of this entirely zero-shot from text prompts. We evaluate using a diverse object set, varying the objects to manipulate and the receptacles for every task, with strong pose randomization to ensure that we're really stress testing ManipGen's generalization capabilities. Note, we did not directly train on any of the objects we evaluate on. Instead, by training local manipulation at scale, ManipGen is able to generalize broadly.
So compare this to Aloha Unleashed, where the training is on exactly the objects that they will be manipulating.
In terms of numerical results, we showed that our method beats out some very relevant baselines in terms of text condition manipulation. We include the success rate per task as well as the average number of stages completed, essentially logging the average progress along the task. We also have more results in the paper with comparisons and simulation, as well as more real-world tasks, comparing against end-to-end RL, BC, task and motion planning, and more.
Okay, let me stop here, but I mean, some of these are quite famous and well-known systems, OpenVLA, SECAN, etc. So I haven't gone into the details of are these comparisons actually fair, and you can judge that for yourself. I pass no judgment on that, but at least going by this table, it's pretty impressive. And as I said, this approach is not rocket science. To me, this is obviously the one that we should do. It's like the straightforward thing, right? It's not the complicated thing, it's the straightforward thing. Okay.
LLM-based planning methods. And with that, I thank you for listening, and for additional details, including videos, experimental setups, and implementation details, please check out our website linked on the left and read our Twitter summary on the right.
Okay. So let's go back to this, and okay, so that was the cover, and let me go to the so we can look at this further. So what are the stages? Essentially, learn. I mean, the heavy work is being done by RL, right? RL is providing. So you're developing skills for picking up for different kinds of shapes of objects. So that is being done by RL, right? And so forth. And it should not be just pickup; it should be other skills as well. So what can you imagine as a generalization of this? So here there are only a few skills: pick up, place, open handle, and so on. So the set of skills demonstrated here are far fewer than you saw in the work from Google or the work from Pi. Okay. What I think so just grant them that if we are comparing apples, it's comparing apples to oranges. So the range of skills here is far limited. However, in my view, they meet these two criteria of generalization and robustness in much better. I'm more satisfied with that. I like the overall hierarchical structure of this because I don't think we can solve large-scale robotics problems without having some notion of hierarchy. Okay. I think they use a language model in the right way. I mean, often there is work which uses LLMs for the lowest level stuff of, joint angles. That to me doesn't make sense. But using language for the higher levels of planning is totally sensible. Okay. I mean, there could be versions on that theme. There are some versions where you generate a program and execute. I mean, all of that is fine. I think the way where they've used GPT for in terms of visual recognition, where they've used grounded SAM, these are all, I mean, you can try this or that, those are all choices that people might make differently, but that seems sensible. So they have a slide which is on, I think this is the one which has the bold numbers, and I don't want to stand by this because I'm not, actually read the paper carefully enough to see whether I believe that this experiment has been done carefully, but at least the claim here is quite bold because this is like a small team doing something as opposed to a big machine. So let's discuss this for a bit. If I have time, we may go into talking about the line of work from NVIDIA, which has also consistently, they have a series of papers which are in the simulation paradigm with RL. And I think that work is to be taken seriously. But I started with this paper because it's like one paper to read and one talk to listen to. But let's do a discussion first. Comments, opinions, criticisms? Yeah.
Generalized comes out of the way you design the problem, like you divide it into abstractions. But
yeah. So the generalization is coming at the skill level. At the higher level, it's sort of there's vanilla thing which people 50 years ago would have said. You're going to have some operators and you're going to chain them together in some plan. I mean, that is no. I mean, doing it with LLMs is the current way of doing it, but all the generalization is happening at the individual skill level. So when I pick up an object, I manage to pick it up, whatever the object is and whatever the clutter is. Yeah.
But what is unclear is as your data sources become more diverse, then these abstractions keep on holding or they start limiting. Like as the number of skills increase, as the number of like the diversity or the complexity of the scene increases. For example, in all the skills, they never dealt with collision. So for example, if you have to open a cabin or like open a door, but then they just assume that their hand is not going to collide. What if there is something they have to? And like this is just one example, but there are like a million.
No. Let's take that example. So I would argue that, I mean, and this is for everybody, for this approach, the previous approach, right? This is essentially that when you are executing, things can happen that you had not anticipated. Okay, how do you deal with that? And I would have to give the party line answer for both approaches. The party line answer for the teleoperation with has to be, okay, well, if we run these teleoperations a million times, then those kinds of errors will also occur and we will deal with them. And then we will have that in our training data. The simulation people have to say the same thing, which is that when I'm doing the task, I'm going to perturb in various ways, and those perturbations are going to provide the diversity. So both have to give the same answer. I'm not sure. I mean, and both of these in theory can deal with it, but in practice, how well it works, I don't know. Yeah. Tara.
So at a high level, I agree with what they're doing, like in terms of factorizing problem workers, but more so like in terms of both the method and the experimentation. Like one for the method, one thing that they don't like talk about very much is the fact that in their paper there's like a sentence where they talk about, for example, how like for pre-grass poses for both the pig and grass task, they actually use contact grass net as a prior, which is a very good paper from NVIDIA that's like this like, you can just zero shot put in any environment for parallel geographers. So they're heavily relying on other people's like innovations with parallel geographers grasking techniques. And so that actually carries a lot of their skills. So that kind of begs the question.
No, but Tara, let me stop you there. That to me is not a bug, it's a feature. I think that there's this line from Newton. Only reason I've seen further than others is because I've stood on the shoulders of giants. Okay. And the old joke goes, it's better to stand on the shoulders of giants than to stand on the toes of their feet, right? Okay. So then to step on their toes, right? So if you can find a way to use modules that have been trained with a huge amount of data by other people, I mean, it could be real data, it could be simulation, that to me is a positive thing. Yeah. So, I mean, it may be that it diminishes the delta of this paper. That's okay. But I don't regard using a pre-trained module as a negative thing. I think to me that's neutral. If at the end you get the job done better, great. Okay.
You can just localize up to what point you should reach, because they factor in their policy, like they have an equation where they multiply like the pi reach by the pi like local policy. And what I was saying is like, why don't you just reach and then activate contact GraphNet once you want to start graphing locally? Or for doing the articulated object stuff, for like graphs being handled and opening and closing doors, there are already a lot of really good models of parallel geographers that have been trained on the same data set like PartNet that they use. So you don't even need these RL policies. I don't really see the point of the RL or even the dagger, because you can just activate these when you know them, since you have 5 predefined skills. That's what I was gonna say. Like, why not just use those straight off?
Okay.
And then the other issue with it that I had is like, when they do, so first it's like in terms of the experimentation, like the baselines, like for example, like Saycan uses Palm as its LLM, whereas they're using like GPT-4o. I feel like it would be more fair if they plugged in GPT-4o and like any other better vision stuff, because like Tidy, that task, and Cook are effectively just like industrial bin placing tasks, right? Where the bin for Cook is like your big pot that they put like corn or whatever in, like they have a big husk of corn that they grab and place. And Tidy is just, they pick and place 4 objects. That's why it's called 8 stages, because you do pick and place times 4. It's why is Saycan getting 20%? That doesn't really make much sense to me. It's, you could use so many like older papers from like 5 years ago to do their hardest tasks. I don't really understand these numbers. And then like, in terms of the setup, like they have like 5 cameras, right? Like they have the wrist camera from Uni, which they use for like activating the local policy, because they have this whole like ableation on how important the size of that local crop is. And then they have like 4 cameras at every corner. And the reason why they excel so much in like these tasks that have the shelves and the like the replaced cabinet floor door floor is because their like motion planner neural MP was heavily like trained on these sorts of tasks. If you look at the neural MP paper, which I've also read and talked about. So like it's just like I think it needs to be like the method. I'm not convinced by it. I'm not convinced by the experiments either. Like they don't make very much sense to me, because they're using way more advanced vision and language tools. I think if you just replace those in, like especially with box poser too, like if you look at box posers from like Gideon and Pepe, like they do a lot of stuff with articulated objects. It's just that the way they train on the articulated objects is for different types of tasks, right? But they also deal with opening and closing doors and stuff like that. I'm sure if you just use similar environments to what they have and like retrain box poser, it would work well, because their setups for these experiments looked identical to the neural MP paper.
I see. Okay, so I think you made a couple of different points, so let me unpack them. So one is specifically about this comparison to other work, which, as I said, I don't want to defend because I did not read, and your critique may well be quite correct. It's a standard. It's a challenge, really. So what I want to bring up from that is like the challenge of doing robotics work, because in computer vision, when we do comparisons, we have exactly the same data set. So with which, so you take your new technique, you run it. I mean, it's exactly the same data set. Here you have, if you want to do experiments in the real world, now you are getting the class of scenes that these folks are considering are different from the class of scenes that Voxposer was considering, which is different from the class of scenes that Saycan was considering. So you essentially have these domain shifts in the lab setup, and those are favoring one approach or the other. So I mean, this is like a scientific replicability problem that bedevils robotics research. I mean, it's true. I mean, okay. Then there was this issue of what how much juice was there in their skills, right? Essentially, and that there were pre-trained quote sort of foundation models of skills, right? Like something for grasping, whatever, that can do 99% of the work, and maybe what they added was very little. Now that's a that's a good point. So that they should really have addressed by doing suitable ablation studies, because that I can see that there's an experimental, you can do an experiment with that. You can do exactly, you can just see how much did I gain from using my RL policy versus what I would have by just taking a previous approach. So this is a very valid point. There's a third point which you made about experimental evaluation, which is a critique which is true of both work across AI, which is that we run these experiments comparing to some older paper, and in the meanwhile, many things have improved. And your paper has all those newfangled things, and that old paper has all the old stuff. So maybe you're using a much more powerful LLM, maybe you're using a much powerful segmenter, maybe you're using a much more powerful recognition engine, etc. And this is a challenge also for computer vision systems. So there was a very nice paper from Serge Belanger et al., which was on this task of metric learning, where people had been writing papers for years, and they all, of course, to be published, they were better than the previous year's papers. So what they did was they just re-implemented all those papers, but using the most modern techniques for how to train a network, the size of the network, the augmentation, etc. And then they found that all those approaches were equivalent. So there was an older paper which was simpler and which actually worked as well. Okay, and this is sadly true. Okay, because what's happening over time is that we improve many different aspects. We improve our data augmentations. We improve how we initialize our neural network. We improve our training recipes. All of this, right? So therefore, the experiments are never in comparable conditions, and maybe there is an aspect of that here. Yeah. So this casts some concern. Yeah. Continue.
Section is like, oh, we didn't do this in a closed loop way, but that's like true and false. They didn't do it in a closed loop way in terms of like every time they would decide to go from one stage to the next based on what the planner gave them, they wouldn't check if they were successful. But the perception was closed loop because they do mention that like grounded SAM has issues. So they would pass back grounded SAM outputs to ChatGPT 4.0 until they would like line up. So the perception was like closed loop in a way.
Which is okay, right?
Okay, but like that helps a lot too.
No, yeah, but no, but those are quote hacks which I regard as legit, right? Maybe they should have been more honest in stating that, but I regard those as legitimate because those are scalable. Presumably, you could do that every time.
The failure cases for their baselines, it has a lot to do with like perception.
Okay. Okay, that's fair. More comments, other comments? Yeah.
So how do you test the generalization, or how do you define the generalization of skills? Like in different objects? Or...
Okay. So Yutong's question is, how do you test the generalization of scales? Yeah, so for me, the test is many different objects. So I mean, a good example of this is the paper we had with Housey. He's rotating objects, and he rotates like, they all, I mean, we could not have rotated an object which was like a 1 foot basketball or something, right? The basketballs are not 1 foot, but a 1 foot globe. We couldn't have done that because in the hand that doesn't fit. But of objects of the size, which is something like 5 centimeter by 5 centimeter by 5 centimeter, in this kind of zone, we tried many different objects and it worked across them. So I think that, to me, that's a requirement. I mean, you're doing a robotic scale, it should work across many different objects or many different sizes and shapes and friction properties and so on.
For example, grasping a cup or opening a drawer to be transferred.
No, they're not exactly the same. So there will be, so it's like, but when we are recognizing dogs, we have many different breeds of dogs. So in fact, the operation of, say, pushing an object, if the object is very heavy, pushing an object is very different than when pushing a small object on a desktop. So in our language, in the English language and in other human languages, we use verbs which are with a great amount of generalization inbuilt into the definition of the verb. So there's generalization with nouns too, right? Because dogs, I mean, it's a category. There are many different kinds of dogs and different poses and everything else. But when we consider verbs like insert or push or throw, there can be many different physical ways of doing it. So just like the pixels are not the same for different kinds of dogs, the motor actions are not going to be the same for different kinds of throw, different kinds of insert, and so on. But we must generalize. I think this is what we believe to be important and true, right? We must show how to generalize. More questions or comments? Okay, so let's, I have, how much time do I have? I have like 7 minutes. I want to go and spend a few minutes on that NVIDIA website, because I think that gives you another flavor of this line of work. So, okay, to just close out on this paper, I never pay very much attention to the details. I think the important thing always is the overall philosophy. If I like the overall philosophy, that's what I'm trying to convey here. I like the overall philosophy of this paper. All the details will change. Next year, we'll find a different way of doing each of these things. But, you know, there's a quote from Tukey, which I'll state. So Tukey was the statistician. He's one of the co-inventors of the fast Fourier transform. He says, better an approximate solution to the right problem than the exact solution to the wrong problem. Okay, I believe in this. So if you are kind of barking up the right tree and you have something which doesn't work super well, but it's sort of hitting the most important components in kind of the right way, I'm much more, I like that much more, because then I feel, okay, 1 year later, 2 years later, 3 years later, there'll be more work and it'll get better. But if you are fundamentally wrong-headed, okay, then what's not worth doing is not worth doing with great detail and more data. Okay, so I am just stating my philosophical biases here. Okay, so this is the NVIDIA blog. They have a series of papers before this. This is one of I think the last paper in this series, and there are earlier papers. And Toru can add more details because she has hung out with these people. So they took this problem, which I like. Okay, so this is the problem of insertion. Okay, but they're not like taking this Aloha Unleashed and doing it for one particular assembly. They're trying to do it for all of these. So in all of these, there is some part which has to be inserted into some other part. So they call this the plug and the socket. So the plug is what gets inserted into the socket. And then they have all these different shapes. So there's the white bit and there's the green bit. And one of them, the white bit has to be inserted into the green bit. Okay, so before I proceed, what do you think they would have done? What do you think they should have done? You already have some hints. You know that they are into simulation. Okay, simulation makes a lot of use of NVIDIA chips. Okay, they are into RL. Okay, so what should you do? So you have to do, okay, so this paper is called Automate. Okay, so what are their contributions? You can probably see this, a data set of 100 assemblies and ready-to-use simulation environments. And then they train policies for these 100 different tasks. So you could guess what it should be, right? We always know that RL works better when you have access to privileged information. What you really want to say is RL works better when the space is reduced. So when the space is smaller, then you're doing trial and error in that space, and then you come up with the right policy. So in narrower spaces, it's much easier to get success with RL. And then we can train all those, and then we can distill them together into one policy. That's a reasonable strategy. Okay. I mean, that's what you would expect them to employ, right? Okay. So let's see what they do. So deployment of, let me automate assembly skills in simulation, data sets and simulation. What did they do? They provide a data set of 100 assemblies and 3D printable objects, as well as parallelized simulation environments for all 100 assemblies. They are based on a large assembly data set from Autodesk. And then they have plugs and sockets. So this is the picture example of a single environment, and then you have zillions of these going on in simulation. Okay, learning specialists over diverse geometry. So you can call these specialists. So this idea is not that different from what you saw in the previous one. In fact, you also have that when we have our walking work, because we have privileged information, and then we have this Z, which is sort of learned, with which you're learning different strategies for different terrains, right? So what do we need? Generating demonstrations for assembly, integrating an imitation learning objective into RL, selecting demonstrations to use during learning. Okay, here's a cute trick, though it's not, doesn't work fully, but assembly is hard, but disassembly is easy, right? So assembly is like putting things together. You need to get their tolerances right. Disassembly is easy. You can, every kid knows how to break things, but not how to build things. So disassembly is easy, and then you just run it in reverse. So you've got a trajectory. So this is cute, right? Okay, but it may not be right in terms of being a robust way to do it, but at least you get trajectories. So, and by the way, this should remind you of diffusion models. Diffusion models, as you diffuse and add noise, it becomes like, it's like you don't know what, it's just meaningless, but then you can run it in reverse, because every micro step, every small step in a diffusion process is reversible. So I had not thought of this before. So when I read this paper, I said, oh yeah, obviously this is cool. Okay, but this may not necessarily lead to robust strategies for assembly, but still, I think it's cute. Okay, and you can think about this in other settings, right? RL with an imitation objective. Okay, so there, what do? They basically have humans do the task. So we like that, but this is visual imitation. Humans do the task, and then so there's a human task, and then we want to put this on a robot. So these are standard tricks. Dynamic time warping. You have one trajectory, another trajectory, you want to align them, you do dynamic time warping. This is like a classical idea. It originated in the speech community. I think there are probably papers on it from 1960s or 70s. So they do that for aligning trajectories. So take human demonstrations and use that to initialize your RL. So that seems okay. Then so now they've generated these specialist policies. So they actually land up generating 100 different policies for 100 different assemblies. Okay, and they get, what I found was compelling is they do this in simulation, then they repeat the experiment in real, and the numbers are reasonably consistent. So this is good, right? Because one of our challenges in robotics is, how do we do experiments? How do we know whether our work is good? And simulation is much easier and much more replicable, but your simulation results may have nothing to do with real world results. And here they give a fairly compelling example that they give you some flavor of what is happening in the real world. Then we come to the task of learning a general assembly skill. Okay, what do you expect this to be? Essentially, what you expect is, I mean, again, you don't have to read the paper, just think about it and you'll know what they're going to do. I mean, they're going to try to use a distillation. They're going to have dagger in there somewhere. Okay. Once you think about it for 10 minutes, after that, you should go and read the paper and you'll find that they've done more or less those things. This, by the way, is a good device. So let me give you this gratis as advice for research. Whenever there is some topic that you don't know that much about, you read the paper, you start the paper, you read the first part of it, maybe the introduction, understand which is stating the problem, right? And now you shut the paper up. Okay, you go off and you think about it yourself. Spend an hour thinking about how you would solve the problem. Okay, and it may be that for many papers, you may find that you actually find the solution that they find. Sometimes you may not. Sometimes you might find another solution. But very importantly, what you will find are what are the difficult aspects of the problem when you try to struggle with it yourself without looking at the solution. And this is a trick which I learned like 45 years ago from Donald Knuth, one of the founders of computer science. Said whenever any area he doesn't read the solution. He first reads the problem statement. He tries to work it out himself. After he has tried to work it out, then he reads the solution. So this is a good research advice. Okay. Anyway, I think that if you did that, you will find that what they've done is quite sensible. So they've got a set of policies, behavior, and then they use Dagger, which is always the right way to think about robustification, because when you are proceeding on you are executing some policy, things will happen which are unexpected, and you'll go off the path, and you need to recover. And that recovery, this comes very naturally from all the simulation data. So anyway, then they get this generalist policy whose performance decreases a bit, but not too bad. And then there is blah, blah on how they did it, which I will leave because I'm already 6 minutes over time. So thank you very much. Okay.